Hello and welcome to another GCSE revision video, and in this video we're going to be looking at quadrilaterals, and this time we're going to be looking at the rhombus. If a square has been distorted so that its internal angles are no longer 90 degrees, then we have a rhombus. It's basically like a tired square who can no longer stand up straight. Another name for a rhombus is a diamond. So we can think of a square as a special case of a rhombus, one whose angles are 90 degrees. In other words, all squares are rhombuses, although not all rhombuses are square. Just as with a square, all four lengths of a rhombus are exactly the same. Again, just like with a square, opposite lengths are parallel. The opposite angles of a rhombus are identical to each other. We say that they are congruent. It's just a fancy way of saying that opposite angles are the same. Adjacent angles add up to 180 degrees. Technically we say that they are supplementary. Just like a square, the diagonals of a rhombus are perpendicular bisectors. That is to say, they chop each other in two and that they intersect each other at 90 degrees. And when I say chop each other in two, I mean chop each other in two exactly equal halves. Unlike a square though, the diagonals of a rhombus are not the same length. And also, unlike a square, a rhombus only has two orders of rotational symmetry, or the order of rotational symmetry for a rhombus is 2. Just like a square though, the perimeter is just 4 times the length, since all four lengths are the same. However, unlike a square, we can't just square the length to get the area, more's the pity. Okay, so I've drawn myself a square on a grid, and we can see that the square is 1, 2, or so I'm going to say 1, oh, let me use the right colour, 1, 2, 3 units across, by 1, 2, 3 units up. So we would expect from the area of the square to be 9 square units. Well, this is 1 square unit. So we've got 1, 2, 3 square units on the bottom already. So let's say this is number 4, 5, 6, 7, 8, 9. So I'm relieved to see that a square really is 9 square units, which is 3 by 3. So yes, multiplying the length by the width, or rather the two lengths, really does give us the area of a square. So why can't we do that with a rhombus? Well, let's try and draw a rhombus. Let's pick colour blue, say. And I'm going to draw a first length as 3 units across. That's 1, 2, 3 units across. Now, if I try to draw my next one as 3 units up by 3 units across to get my diagonal line, if I go 1, 2, 3 units across by 3 units up, you can see this is an awful lot longer than the base. And the base has to be the same, or the lengths have to all be the same for it to be a rhombus. So how long do I have to draw this diagonal line? Well, let's just zoom out for a minute. And let's do some little calculations on the side here. So let's say we've got a triangle and we're trying to get the longer length, the diagonal of the triangle. So this is my x coordinates along the bottom, and this is my y coordinates up the top, and I want this to be 3 units. Well, we know from Pythagoras' theorem that the hypotenuse squared is equal to the sum of the squares of the other two sides. Now let's pretend that we want this angle. Let's say this angle is, say, 45 degrees. If it's 45 degrees, then the beauty of an angle here, this would be a right angle, so then this angle must also be 45 degrees. And therefore, the x coordinate must be the same as the y coordinate, so that just makes it nice and easy to draw. So in that case, 3 squared is equal to x squared plus x squared, which is equal to 2x squared. Now 3 squared is 9, so 9 is equal to 2x squared, so 9 over 2 is equal to x squared. Let me just get rid of that 2. And therefore, the square root of 9 over 2 is equal to x. Well, the square root of 9 is 3, and the square root of 2 is root 2, which is equal to x. And I know the square root of 2 is around about 1.4 something. Now 3 over 1.5 is going to be the same as 6 over 3, which is 2. So 3 over the square root of 2 is going to be slightly bigger than 2 squares, but not much bigger than 2 squares. So if I zoom back in again, go back to my blue, I'm looking for a straight line that's going diagonally through these. So it's just a little bit over 2 squares to make this length about the same as this length. So then this is going to be, again, at 45-degree angle, which is easy to draw because it's just going through the diagonals, and just a little bit over, so just a little bit over 2. And then we can join that up again with our 3 units. And now if we try to count our area, well, we've got, I'm going to call that a whole 1, 2, 3, and that's 4 whole squares, and these 2 squares are going to equal 1 whole 1 combined, so I'm going to call that a half a square. I'm going to call that a half a square, and I think these 2 squares are going to be half squares, and this is a half a square, and I've got a tiny sliver left over which I'm not quite sure how much that's going to come to. It's definitely going to be a decimal something. So we've got 1, 2, 3, 4 halves, which is 2, plus 1, 2, 3, 4, so that's 6. So this area is going to be 6 point something. So obviously we can't just have the square of the lengths. So how do we get the area? Well, one way to get it is to draw a perpendicular line down from the angle, and that will give us the height. For any quadrilateral, it's going to be the base times the height. So if this is the height, and if I say this is our angle, and we've set our angle at 45 degrees, so this is a 45-degree angle. Now, this height here is basically this length here which is the hypotenuse of our right angled triangle that we've just created, and yes, this is a right angle. And this length here we know is the same as this length here. So we can call that just the base, or the length, whatever. So it's just the length times the sine of this angle. We've set it as 45 degrees, but we can have it anything. So this is just the sine of the angle. I'm going to call it x times the length. Let's write this out neater so that we can actually see what we're doing. I'm going to choose this area here. Okay, so what we're saying is that area is equal to 1/2. What am I saying? Why am I saying a half? It's equal to the length multiplied by the length times the sine of the angle, which is the same as length squared times the sine of the angle. Okay then, so let's see if that works. We said it's a length of 3 and the angle was 45 degrees. So the area is equal to 3 squared, or 3 times 3, times the sine of 45 degrees. Alright, so we calculated that was just around about 6 square units plus change. So let's get the exact answer. So that's 3. Oh, I'll just make sure that my calculator's in degrees, which it is. So it's 3 times 3 times 45 degrees sine, which is 0.707, which is equal to 6.36 square units. So the area of a rhombus is just the length squared times the sine of the angle. Okay, fair enough, you say, but which angle? Well, as it turns out, it really doesn't matter which angle, because opposite angles are the same angle, and adjacent angles have to add up to 180 degrees, which means they're supplementary angles, and supplementary angles have exactly the same sine. So if one angle is x, then the sine of x is the same as the sine of 180 degrees minus x. And if you don't believe me, you can check that out on your calculator anytime you want. Okay, I hope that was helpful. I'd like to wish you all the best with your revision and all the best with your exams. If you enjoyed the video, don't forget to like, comment and subscribe, and I'll look forward to seeing you in another